When a positively charged particle is moving with a velocity v at right angles to a magnetic field B, the magnetic force will have a magnitude of Q times V times B. The direction of the force is given by the right-hand rule, with the thumb pointing in the direction of V, the extended fingers of the open hand in the direction of B, and the force pointing out of the palm of the right hand. If a collection of charges is traveling down a wire of length L with a current I at right angles to a magnetic field, the same magnetic force becomes I times L times B. The direction of the force is still obtained from the right-hand rule, with the thumb pointing in the direction of travel of the current I. In the force experiment of this lab, we use a coil with N turns, with one end at right angles to the magnetic field. The end of the coil that experiences a net downward force is at the bottom horizontal section, with length L. A slight rearrangement of the force equation to this situation gives force equal to N times B times L times the current I. We will be varying the current I through the coil and measuring the corresponding force. We anticipate that a plot of force versus current will yield a straight line with a slope of N times B times L. Here's the setup we'll be using. The coil is hanging vertically from a force sensor placed between the poles of a relatively powerful magnet. Science Workshop measures the amount of force. The power supply is used to adjust the amount of current flowing through the coil. The ammeter measures the current. Notice that the ammeter is in series with the rest of the circuit, and that because relatively large currents are used, we use the yellow hole of the ammeter and set the current scale to read a maximum of 20 amps. As always, the force sensor must be calibrated. First take a zero reading with the coil hanging to nullify its weight out of the experiment. Then add a half a kilogram, call it 4.9 newtons, and take a second reading. When you use the so-called Hall probe to measure the magnetic field between the poles of the permanent magnet, understand that the magnetic field lines must pass perpendicularly through the flat surface of the probe. Give the probe some slight rocking rotations to find and record the maximum value of B from the probe meter. Here we have recorded the force for a variety of currents ranging from 0 through 5 amps. The force sensor electronics make the force data appear noisy, but the mean values are reliable, and the standard deviation is not as large as you might think. A plot of force on the y-axis versus current on the x-axis yields the anticipated straight line with a slope to be compared with N times B times L. We now move on to an amazing experiment that uses the force on a beam of electrons to determine the mass of an electron. A particle entering a region of uniform magnetic field with V perpendicular to B will always experience a force at right angles to its motion, and therefore follow a circular path. Setting the magnetic force equal to the centripetal force gives the equation QVB equals mv squared over r, where r is the radius of the orbit. The charged particles used here are electrons emitted from an electron gun. We can relate the speed that the electrons emerge from the gun to the accelerating voltage using the conservation of energy. The gain in kinetic energy results from the loss of electric potential energy. We can use the two equations resulting from these physical notions to eliminate the unknown velocity v from the expressions and solve for the mass of the electrons in terms of their charge, the magnetic field B, the radius of the circular path, and the accelerating voltage, capital V. We begin by applying a limited voltage to the wire filament, which when heated boils off electrons from the wire. Under no circumstances should this voltage ever exceed 6.3 volts, or the costly device will be ruined. Now apply a large accelerating potential, capital V, about 150 volts, to fire the electrons horizontally from left to right out of the electron gun. This voltage should be recorded with the voltmeter. Turn on the current through the two electromagnetic coils and turn it up until the electron beam circulates. The beam is visible because the electrons collide with mercury atoms inside the bulb, exciting them and causing them to glow as they do in a fluorescent bulb. We can obtain the diameter of the circular beam from the mirrored centimeter ruler behind the beam. If you've ever tried to read the fuel gauge in a car while sitting in the passenger seat, you know that you must look squarely at the gauge to get an accurate reading. The same is true here. Compare the right edge of the beam with the scale by moving your eye until the mirrored beam matches the actual beam at the right-hand edge. This ensures that you're looking squarely at the beam. Now move your eye to the left to match the left edges and take another reading. The diameter is now determined. Go ahead and measure the magnetic field between the coils. Again, slightly rocking the probe to get the maximum reading. But because you cannot reach the center, you'll get a more precise result by measuring the current I and using the theoretical prediction for the B field produced by these two coils of 7.8 times 10 to the minus 4 times I. Now you're prepared to determine the mass of an electron. The last portions of this lab involve measuring the magnetic field strength of various electromagnets. We start with the long straight wire. Here the magnetic fields circulate around the wire with a strength proportional to the current I and inversely proportional to the distance r from the wire. Place the probe close to the wire, oriented such that the circulating B field lines pierce the flat probe surface, and measure the distance from the center of the wire to the probe as best you can. We typically use a more accurate Gauss meter for the long straight wire because the field is so weak. When the range dial on the right is set for a maximum value of 0.3, 3, or 30 Gauss, then the bottom scale is used. But when the range dial is set for 0.1, 1, or 10 Gauss maximum, then the upper scale is used. A solenoid is a helical coil with a strong uniform magnetic field through the center with a strength given by μ0 times n times I, where little n here is the number of turns per unit length. Insert the probe in the slot such that the B field pierces the flat surface and then turn on the current. A circular coil with n turns will produce a magnetic field at its center proportional to n and I, but inversely proportional to the radius of the coil. Again, just make sure that the flat surface of the probe is perpendicular to the magnetic field direction.